Swayam Prabha. Digital India. Educated India.
Last class I have discussed that what are the major parameters for ground motion, and then I have given the expression of simple harmonic motion, and then I have discussed what is frequency, what is amplitude, and what is the phase angle, and then how to represent them in terms of trigonometric notation and then the complex notation. Now today I will start about the strong ground motion measurement, that is measurement of ground motion, how we will measure them. So that means here first the seismographs are used to measure relatively weak ground motion and seismograms are the produced. That means I have shown in the seismograph in my first module that this is your seismograph. So if you place it in different orientation, then you can measure the two horizontal component of motion and one vertical component of motion. Here you will, if you place it, you will get the one vertical component or vertical component of the motion. Now you can place it in different way, you can get the horizontal component of motion. But remember that if you use the seismographs, they are generally measure the relatively weak ground motion and they produce a seismogram. I have shown in the last module that what is seismogram, so where you will get that this P wave, base wave and the surface wave and their amplitude, displacement amplitude, so all you will get that. So now if the accelegrams are generally used to measure the strong ground motion. So this is accelegraphs are used generally to measure the strong ground motion and they produce accelegrams. So seismographs are used for relatively weak measurement of relatively weak ground motion and accelegraphs are used to measure the strong ground motion. Now if I start with a simplest type of seismograph, so that you can see here, which is basically a mass spring damper single degree of freedom system. Now what is single degree of freedom system? So single degree of freedom system, it discrete system whose position can be described by a single variable, whose position is here. Which is that variable? If I use that seismograph, so that variable will be translation displacement. That can be vertical, that can be horizontal also. That means its position can be described by one single variable, and here that variable is translational displacement. Clear? So here only displacement, because we are not measuring that rotation, so it is only in terms of displacement its position is being described. So that's why it is single degree of freedom. Why it is spring mass damper system? So that I will discuss here. Now the relative movement between the mass and the ground is indicated by the trace made on the rotating drum. As I mentioned, there is a rotating drum and this trace is made. From there we can get what is the relative movement between mass and the ground. So this is the mass and the ground. Now if I draw the horizontal position of the position of a seismograph where I can measure the horizontal displacement. Okay. So in that case, this is if I draw the housing. So that housing is actually fixed on the ground. This is my ground and this is the housing. And as I mentioned, this is basically a spring mass dashboard system. So this mass which can move, but it can move in one direction, that is your horizontal direction. And then there is a spring and there is a damper or dashboard. Spring constants K, this is damping C, and now here it is, there is a drum, this is a rotating drum, and that will made this trace. Okay, so this is the horizontal one. This one is vertical, this one is horizontal. So this is a constant mass. So it is moving, and then this trace will give you the relative movement between this mass and this ground. This trace will give you relative movement between mass and this ground. This is vertical one, this is horizontal one. Okay. Now basically here also you can, this is mass spring dashboard or damper system. Now a particular measuring station, 3 seismographs are placed to measure motion in vertical direction and 2 perpendicular horizontal direction. So basically on a particular station you provide 3 seismographs. So one is used to measure the vertical motion and another 2 is used to measure the horizontal motion. Horizontal, these total 3 translational displacement motions are being measured by using 3 seismographs at a particular location. Okay. So now start, this is a spring mass and damper system, and this is also single degrees of system. So let's write the equation of the motion. Okay. So now the equation of motion, okay, subject to external loading. So I can write that this is the mass M and external loading Qt is applied. This mass can move, and there is a spring, so that will give you Fs, and there is a damper, so that will give you Fd. So these are the forces. So you can see this is the damper, this is spring, mass, and external load is applied. So this is your forces. Now where Qt is equal to external load, and there is inertia force also. That inertia force will act here, Fi, as your force is acting in this direction, so inertia force will also act in the opposite direction. So that inertia force is also there, Fi. So Fi is the inertial force. Okay. Now Fs is the elasto or elastic spring force. Then Fd is the viscous damping force. Okay, so now I can write that Fit plus Fdt plus Fst, that is equal to Qt. Okay, that I can write. Now how I will get that F1, Fi, Fs, Ft? So from Newton's second law that states that the inertial force acting on a mass is equal to the rate of change of momentum. Okay, so rate of change of momentum. So in that sense, I can write that Fit, that is equal to rate of change of momentum. What is momentum? Momentum is equal to your mass into velocity. So here this will be mass into velocity. Velocity will be dut by dt. If your ut is the displacement, if your ut is the displacement, then u dot t, that will be equal to dut plus dt, that will be your velocity. Okay, and your m is constant rigid mass. Okay, and it's Newton's second law says it's the rate of change of the momentum, and momentum means there is mass into velocity. So if I say the momentum that is equal to mass into velocity. Okay, so that means you can see that that is the rate of change. Rate of change will be d dt. So finally I can write that Fi t, that will be equal to mass into d square ut, because mass is constant. Okay, it's not changing, so that means d dt into du dt, so it will be d square u dt square, and which is nothing but the acceleration. So that means I can write this will be m double dot t. So your d square ut by dt, that is your acceleration. And I have discussed these things previous class also. So I will get that Fi is equal to m double dot t. Similarly, for damping force is proportional to the velocity of the mass in case of viscous spot. So my damping force, that will be proportional to the velocity of the mass. So this will be proportional, and this is the proportional constant c. So this will be velocity. Velocity will be du dt. So that will be equal to c u dot t. Okay, where your c is equal to viscous damping coefficient. And that is for dashpot. Clear? So now the next one is that your FST, that is the product of stiffness and the displacement, because this is your simple K into U T, because this is elastospring force, that will be K into U, that U is the displacement. So now if I put this all expression here, then this will be M double dot U plus C dot U plus K U T equal to Q into T. So, this is your basic equation for motion if it is subjected to external load. Now, in case of base shear, what will happen? Suppose your equation of motion, now I can write the equation of motion when it is subjected to base shear or base shaking. Subject to base shaking, what will happen? That this is your mass, say, and this is your springs, it is K by 2, K by 2, and this is your dashpot. Now, when there will be base shaking, what will happen? There will be a relative movement. What is that relative movement? That it is the initial position of the mass. Say this is the initial position of the mass. Okay. When there will be a base shear that will act here, then it will change the mass, will change its position like this. Here also it will shift. Okay. So, this is the displacement of base or the ground, and this will be the displacement, because this is the displacement ut, and this will be the total displacement utt. Okay. So, let me discuss what is this ub, u and ut. Okay. So, now your u, okay, let me use this another page. So, ub t, that is equal to base displacement. Okay. So, when there will be a base shaking, so this base will displace, so that is the base displacement, and the ut is the displacement of the mass relative to the base. That means is the relative displacement of the mass with respect to base. So, you can see this is the relative displacement, this is total displacement, this is your base displacement. So, this one is the relative displacement of the mass with respect to base, okay, related to base, and then the ut is the total displacement of the mass. So, I can write that the inertial force that depends on the total acceleration of the mass, but the viscous damping force and elastic spring force, they depends on relative velocity and relative displacement respectively. So, that means the displacement, viscous damping force and the elastic spring force, so they depends on the relative displacement and the relative velocity, but the inertial force, they depends on the total acceleration. So, if we write in that way, then I can write m, acceleration will be total, this is inertial force, so this will be ut double dot. So sometime I can write ut t or sometime I can write ut, both are same, it's function of t. Then for other two cases it will be only the relative, that will be only u. So it will be c u dot, then plus k u, that will be equal to 0. Okay, because it is only base shaking. So now we know that u double dot t, that is equal to actually u double dot b plus u double dot, okay, summation of that. Now if I replace that, m u b double dot plus u double dot, then this will be plus c double dot plus k u, that will be equal to 0. Now if I write that, then I can write m u double dot plus c u dot plus k u, that will be equal to minus m u b double dot. So what this equation indicates? That equation indicates that you are applying an external load. If you compare these two equations, this equation and that equation is the same. So only it is indicate that you are applying a negative external load of m u b double dot amount, that it's indicate. Now here, from here, how can I correlate these things with our this case, ground motion case? So here I can write this similarly. I can write this will be m u double dot plus c u dot plus k u, that will be equal to minus m u g double dot. Okay, so what is that? That u is equal to the seismograph trace displacement. That is your relative displacement between the seismograph and the ground. This is also, u is also relative displacement of the mass. Okay, the relative displacement of the mass and the base. So here also u is the seismograph trace displacement, that is relative displacement between the seismograph and the ground, and u g is equal to the ground displacement. Okay, now this is your basic equation, and where this u is the relative displacement between the seismograph and the ground, and u is the ground displacement. Now how I can measure this ground displacement or ground acceleration? By using these two equations. So these two equations you can derive from the basic equation that I have given, but I am not giving the derivation here, I am just giving you the final expression. Now if the ground displacement is simple harmonic motion at a circular frequency omega g, then the ground displacement amplitude ug or ground displacement ug can be measured by displacement response ratio or by measuring trace displacement amplitude u. So if you know this equation, here what is the b? Beta is the tuning ratio, which is omega g by omega. What is omega? 0. Omega 0 is the undamped natural circular frequency that can be determined by root over k by m, and zeta is the damping ratio, which is C by 2 root over Km, where Cc is the critical damping, which is 2 root over Km. Actually, damping ratio is the damping divided by critical damping. So here critical damping is 2 root Km. So for a this mass spring dashpot system, we know the K, we know the M. So we will get what is critical damping. We will get what is the undamped natural frequency. So we can get, if you know the gamma g, then we can get the beta. We will get the damping ratio. We will get the natural frequency, undamped natural frequency. So if we know all these things, and if we can measure the trace displacement or the relative displacement between the seismograph and the ground, then by using this expression, I can determine what is the displacement of ground, UG. Similarly, by using the second expression, the acceleration response ratio, and again if I measure the trace displacement amplitude, then I can determine the ground acceleration also. So from the second expression I will get the ground acceleration, and the first expression I will get the ground displacement amplitude. A second one I will get the ground acceleration amplitude. Okay. So and this way I can measure this ground acceleration amplitude and the displacement amplitude. Or if you measure the acceleration, then if you integrate it, you will get the velocity. You can also get the velocity, and if you further integrate it, you will get the displacement also. Now, what are the different types of accelegraph, or sometimes it is now called the accelerometer. So this is a servo accelerometer that can provide good accuracy over the interested range of frequency. That means the frequency range of this geotechnical earthquake engineering interest. So those within that interest range, you will get the good accuracy if I use the servo accelerometer. Now, piezoelectric accelerometer is particularly useful for high frequency measurement, and triaxial accelerometers, the three orthogonal component of acceleration, two horizontal and one vertical, are measured with a common time base. So these are the different accelerometers that are used. Now, as I mentioned that what are the parameters we have? We have amplitude, frequency, and the duration of time. Okay. So these are the three major parameters of ground motion. Now, first I will start about the amplitude parameters. So these amplitude parameters are acceleration, velocity, and displacement, or sometime all. So if you know the acceleration, you can go to velocity by integration, and if you further integrate it, we will get the displacement. So this all are three. So first we will go for acceleration, then we will go for velocity, and then we will go for displacement. So basically we are measuring acceleration or velocity or displacement by using your accelerometer. Okay. So and for weak motion is seismograph. So now first we will discuss what is peak acceleration. Now peak horizontal acceleration, that is PHA, or sometimes it is called PGA also, peak ground acceleration, simply the largest absolute value of the horizontal acceleration. Here you can see it is the largest value of this peak. It is largest one, but it is absolute means it is positive negative. So I will take the absolute one. Largest value of horizontal acceleration. Okay? In earthquake engineering, vertical acceleration have less significant than the horizontal acceleration, but it doesn't mean that always you will neglect that. Sometimes we neglect that as it has less significance compared to horizontal acceleration, so we neglect this vertical acceleration, but not always. Okay. For engineering purpose, the peak vertical acceleration can be taken as 2/3 of PHA. There is a thumb rule that if you want to take it, you can take the peak vertical acceleration as 2/3 of peak horizontal acceleration. But remember that peak vertical acceleration is generally greater than 2/3 of PHA near the source of moderate to large earthquake and less than 2/3 at large distance. So that means this is the thumb rule that you are using 2/3 of PHA, but it is also not always true. Okay, so that means if you want to use, first of all, generally we neglect it, but as I mentioned, is not always. And if you want to use the PVA, then you take the 2/3 of each. But in addition to that, you take your own judgment that where you are using it. If it is far away from the your earthquake, moderate to large earthquake, then it can be less than 2/3 also. But if it is very close to that source, then it can be more than 2/3 also. Now next one is the amplitude, this amplitude parameter that we are talking about. So this peak acceleration, we can continue further, that ground motion with high peak acceleration are generally more destructive than the motion with low peak acceleration. It is quite common that if we have a higher peak acceleration, then that will create more damage or destructive than the motion with low peak acceleration. Okay, but it is not always true. It is not always true, but not always true. Why? Because the earthquake with high peak acceleration may cause no significant damage to structure if the peak acceleration is occurred for a very high frequency and the duration of earthquake is small. Suppose your frequency is very high and the duration of earthquake is small. In that case, high peak acceleration may not create a significant damage to the structure. So it is okay that your motion with high peak acceleration will give more damage compared to the motion with low peak acceleration. But sometimes the case where the high peak acceleration may not cause significant damage if the peak acceleration is occurred with very high frequency and the duration of earthquake is very small. Next one is the peak velocity. You can see this is the curve for peak velocity. This is velocity versus time plot. Previously one, this is the acceleration versus time plot. This is the plot we are actually getting from the instrument. Okay, this acceleration versus time, and or from there you can go the acceleration velocity versus time, and or you can get the displacement versus time also. So these are three things: acceleration, velocity and the displacement. Now the velocity is less sensitive when ground motion has higher frequency content. So it is a higher frequency content is there, then velocity is less sensitive. But where the velocity is more sensitive, the peak horizontal velocity PHA can characterize the ground motion amplitude more accurately in intermediate frequencies than PHA. So if it is high frequency content is there, then pH is more significant. But if it is intermediate frequencies range, then PHV, the peak horizontal velocity, can characterize the ground motion in better way as compared to PHA. Clear? Then the proportional of damage of a structure, those are sensitive to loading in the intermediate frequency, that is the tall or flexible building or bridges, may be indicated more accurately by PHV as compared to PHA. So as I mentioned that PHV can characterize the ground motion in better way if it is in intermediate frequency, then structures those are sensitive to loading of intermediate frequencies like stall, flexible building, bridges, there the potential damage of the structure may be indicated more accurately by PHV as compared to the PHA, because PHV is more sensitive in the intermediate frequency range than your PHA. Intermediate frequency range. Now peak displacement. Okay. So this is you can see for a site, this is your acceleration to different site, acceleration and time. This is the velocity versus time. This is displacement versus time. So here acceleration, peak PHA is more. Here your PHA is less, but here velocity is more, second side, compared to the velocity. PHV is more compared to the first side. Here this is the displacement of two sides. Okay. So, and then when you are talking about the peak displacement, this is generally associated with the low frequency component of the ground motion. The peak displacement is less commonly used than peak acceleration or peak velocity, as peak displacement is often very difficult to determine accurately. So, it is very difficult to determine accurately. That is why it is less commonly used than peak acceleration or peak velocity. Okay. So, generally peak acceleration or peak velocity is used, as it is difficult to measure. So, that means if I summarize that if your high frequency zone, then your PHA is more sensitive. Then if it intermediate zone, then your PHV can characterize the ground motion in better way. But if it is very low frequency component, then this peak displacement is associated with in this range. But that peak acceleration PHA and peak velocity PVA are generally more frequently used as compared to the peak displacement. Okay. So here I am finishing the today's lecture. The next lecture I will discuss that what are the other amplitude parameters and how we will estimate those parameters. Thank you.